Okay, I'd like to introduce our next speaker, Sottile, who will be talking about critical points of discrete periodic operators.
Oh, well, thanks a lot. Thanks for coming. I'm going to do a tiny bit of advertisement first. I want to point out, so sorry, this is everybody, most everybody should be interested. There's a conference that has been going on for now 30 years called MEGA. That's the English version of that's the Romance version of effective methods in algebraic geometry. It's been going since 1990. Happens every other year. This year it's going to be in Leipzig with the university and the MPI, and at the end of July. And the reason I'm talking about this right now is that it's a refereed conference, which is not typical in mathematics, but it's typical in other subjects. In that, in addition to plenary speakers, I guess they're not listed here. Maybe I'll show you the poster. We have excellent group of plenary speakers. Unfortunately, this is not.
They're at the bottom of the website.
The bottom of the website. Okay, thanks.
Yeah, there.
Where?
There.
Oh, okay, super. Yes. Sorry, that's kind of small font. Some with really bad eyesight, I appreciate. Yeah. So 9, including people you. Yeah. So you see the now. In addition to the plenary talks, we don't know the number, usually 20-odd contributed talks, and these are refereed. So you submit a paper or an extended abstract, and there's no obligation for any publication or something. It's just to decide on who will speak at the conference, and it should be a great conference. A lot of good people there. But the point is the deadline is the 1st of February, but as is always the case yes, it will be put back at least a week. That always happens. It's like I have to say. So we're not about to break rules. And for more, you can see Simon Kaja Kubias is coming later, and Tomasz Szemberg. He ran it a couple of years ago in Poland. An excellent conference. This should be a lot of fun. A lot of people like Leipzig in the summer. So sorry about that. Let's get back to what I was supposed to be doing. Okay, so this is some work that I've been doing for some time. It's actually the motivation comes from mathematical physics, but it's purely algebraic geometry and combinatorics. I'm going to talk about mainly about one particular project that I've done with Matthew Faust. Math is over there, and it's on the archive. It should be accepted finally by now. It's interesting when you go to another subject and write a paper that uses your tools and perspective, and the people in the subject don't necessarily know this so well. I mean, for instance, I had a referee report that didn't like how I quoted Bernstein's theorem in the quote of the Wikipedia page, which is wrong. So one of the more interesting referee things I've had. So anyway, so it starts out. It starts out mathematical physics. We want to understand the spectrum of a Schrodinger operator which acts on complex valued functions in RD. There's a particular model we're looking at. I'm not going to talk the physics end because though I have a degree in physics, that was 40 years ago. So here the Laplacian is the usual Laplacian, and V is some real value potential. Now this operator turns out is self-adjoint. Acting on L2 functions in RD, and so it has a real spectrum. That's you probably know that from linear algebra. Now, solid-state physics compels you to look at this in a crystal where there's some periodic structure, and also the Laplacian might be perturbed to reflect some periodic anisotropy. You can imagine, and everything is periodic. So there's a translation action of Z to the D on R to the D. D is 2 or 3. Or it could be 1, but the idea would be set up in general. So in this case, I think this is So this is a union of intervals in R, and you have a familiar structure of energy bands and energy gaps. If you looked at like maybe high school solid state physics, where you learn about transistors, that this arises from this structure. Now, spectral theory is typically approached through analysis. L2 functions, operators. Hilbert spaces, but when we discretize this, which is a reasonable approximation. People have been doing this in physics for a long time. It brings into the realm of algebraic geometry, algebraic combinatorics, and computation, and that's what I'm going to talk about today. So discretization is you replace r to the d by a graph which has vertices, which you think of as modeling, say, positions of atoms, and edges, which model interactions between them. And then there's a free action of the free abelian group z to the d on that, which models the translation. And here's two such graphs with there's Z2 periodic. The first one is the molecular structure of graphene, and the second one is some abelian cover of K4, if you want. Now the potential in this case should be, and I've also indicated the actions of the generators of Z2 on that. So the potential should be invariant under the group action, and you also have invariant edge weights. And I'll just write C for that package of the potential and the edge weights. And then in this case, the Schrodinger operator, it's just a difference operator. It acts on functions. I mean, you can see I've already gone into the world of algebra here because I don't care about their square summability property, although it's in the background here. It acts on functions as a potential plus a perturbed graph Laplacian. So the value of LC at F at a point U in the vertex U is, well, you multiply it by the potential, and then you look at the interactions and you take a look at the difference of the value of the edges and add that. That's a modified graph Laplacian, and the perturbed graph Laplacian is this anisotropy that I talked about. And there are many flavors. You could have a Laplacian where the edge weights are all one. You could have no potential or potential. People sort of choose which they want to work on at a given time. Now, so that doesn't look okay. It is a linear operator and bounded on something, but it's not very much algebraic geometry. But this operator that wrote down, it's a self-adjoint operator on L2 functions from the vertices of the graph to the complex numbers, and it commutes with the ZD action, and so what this means, if I apply Fourier transform, I'm going to get a reasonable operator on the transformed functions. So some definitions, I want T to be the unit complex numbers, and then T to the D is a set of unitary characters of my group. And I'm going to use the usual multivariable multi-index notation for exponents. So if you take this is the value of that character. So you take a character, take an element of Z to the D, and then that element goes to Z to the A. Or, I'm sorry, the integers to the D, and that's just simply something in the circle group. Now Fourier transform, which I will not write down, it transforms us to functions which are their f hat is a function from the vertices of the graph to this L2 space on the torus. There's a lot packed in it. It has the property where so this direct sum W, please ignore for a moment. It's really a map from the verse. Yeah. I'm sorry. A lot is packed into this, and I just recently rewrote this. But you get our functions that are on the torus, and they're quasi-periodic in that if you translate a vertex, then this weight Z to the A comes out of that. And because of this, you can pick a fundamental domain of your action, and this becomes an isomorphism between your original L2 space and this finite dimensional, it's W copies of L2 of T to the D. So, okay, now there's a lot of analysis in there, and again, W is as I said, it's a fundamental domain for the action. It's just this set of orbit representatives. And when you do this, and you play everything out, you get that a very simple expression for this operator. So f hat is, again, it's one of these functions. It takes a value at u, which is a square interval function, but the value is simply you scale it by the potential, and then you sum over all the edges adjacent to your point u, and it's the same expression as before, except for I have to use the quasi-periodicity here. But now, if you forget about what the functions are, what you see is this is multiplication by just a matrix of Laurent polynomials, and so it becomes algebra, and it's a fairly easy to understand matrix of Laurent polynomials. This is an input from physics and into this. Now the block variety, which is an object of interest, it's defined by the dispersion polynomial, which is the characteristic polynomial of this matrix. And for points in the torus, it's because we have this property. So if you take the transpose, LC of Z, you get LC of Z inverse, and that's because we have an undirected graph. I mean, that's where it comes down to. I'm not going to explain why, but that means that it's a Hermitian matrix, and so for every element of Z, you have exactly W many real eigenvalues, and in particular, so this block variety, it has this property that is extremely real. So I've drawn a picture of this where a graph has two vertices in the fundamental domain. I've unfurled T2 to be a square, and so for every point in T2, there's two eigenvalues above it, and you get a surface like this called the block variety. Physicists like to think about each sheet as a separate function, but since I want to complexify, that makes no sense. Now, the purpose of all this is the spectrum of the original operator, which you can go back to your analysis and think about what it means. It's the projection of this block variety onto the vertical axis. So when you've done this transform and you're thinking of this in this way, these are in this transform set. These are actually eigenvalues, even though the spectrum is typically not an eigenvalue of an operator, if you know that. And so we start out with a matrix of Laurent. We have a matrix of Laurent polynomials. We have an algebraic variety lying over the spectrum. It turns out because of this, the spectral theory of discrete periodic operators can be studied using algebraic geometry. And I'm going to discuss some results in this program. I mean, it's not. I say early, but it's actually not that new, as you'll see. But here are some questions that you could ask. There's something called the density of states, which is the spatial density of the eigenfunctions at a given energy level, lambda. And Cosmas Scriveris, who was an undergraduate at Texas A&M, he observed that the set of eigenfunctions that at or below at a given energy level is a finely generated module over the Laurent polynomial ring, and he studied this using free resolutions, which he taught himself. There's the level set at a given energy level is called a Fermi variety. That's their terminology. And natural physical questions ask about the irreducibility of both the block variety or the Fermi variety. It being irreducible prevents, for the Fermi variety, it prevents undesirable physical things to hold. So it makes things pleasant in their world. There's a conjecture. So is that if you take a general operator on a graph, this conjecture is also standard in the original setting of crystals, that the points above the block variety, above edges of the spectral bands. Let me just point that out to you. So you see that there's this map. Lambda is this horizontal map, and the image are two intervals. And so you take an edge of an interval and you look at the inverse image, and that's called a spectral edge. But you look above it, and you see that this is a fairly nice smooth function there. It has a non-vanishing Hessian determinant. Right? So it's a reasonable quadratic form, and that's, well, in fact, in this case, lambda is a perfect Morse function, but it's conjectured that these are non-degenerate extrema of this block variety, and that's absolutely necessary for a number of physical properties that all physicists assume. So it's actually assumed in physics, but it's not proven in general, this conjecture. And as I said, many physical properties rely on this assumption, but it's largely unknown even for discrete periodic operators. And there are other inverse problems of identifiability. You have this geometric object, and you like to understand whether this determines the parameters or not. I mean, this was actually something that Carlos talked about, sort of identifiability, but that's the point of some of these estimations. And there's something called existence of flat bands, and there's many questions that can be expressed in terms of the geometry of these objects. So, well, for me, so the first thing is to maybe complexify it to make it a little bit easier. And so we replace the potential and the edge weights by complex numbers. They're just parameters. Now we're going to complexify the compact torus by the algebraic torus. And to understand why I call this a complexification is normally when you think about the real points of the complex torus, you think of the non-zero real numbers. But that's but that's that's not the only way to think about reality in the complex numbers. There's a real structure on a complex variety is simply an anti-holomorphic involution on it. So if you have an involution, you can twist it, you can compose it with complex conjugation, and you get a new real structure. In this case, a very natural real structure on the torus is to take z goes to z bar inverse, and the fixed points of that are exactly the unit circle. So that's I'd like to think of it alternate reality in nature. And now because this operator behaves, its transpose is just simply z goes to z inverse, and if the potential and the edge weights are real, then the dispersion polynomial, not the operator, but the polynomial, the determinant, is stable under this involution, and so its zero set is a real algebraic variety in this sense. Or better yet, the real block variety are the real points of this real algebraic variety called the complex block variety. And it also, because of this property on the operator, the Newton polytope of this polynomial is centrally symmetric in Z. Here's an example. This is d equals 2. The Z exponents are horizontal, lambda is vertical, and this is the Newton polytope of some operator. And you see it's centrally symmetric. Those are just some things to point out. So the Newton, I'm sorry, I should explain. The Newton polytope, one has a polynomial in some known variables, and you ask and you look at the monomials which occur. They have an exponent vector, and you plot them, and then you take the convex hull, and that's a discrete invariant of any polynomial. So I should say that what I'm talking about right now is not so new. I mean, as in the 1990s, Giesinger, Knurr, and Trubwitz, they studied a particular family of these. They studied the Schrodinger operator. This is where you have the edge weights are all 1, so you just have the graph Laplacian. And they studied it on grid graphs, but where the underlying graph is Z2, where you have adjacent, we have edges connecting adjacent integer points, but the action is expanded, where A times in one direction, B times in another direction, and they want them to both be relatively prime. I mean, the results are much easier if they're relatively prime, and that's what they dealt with. And in this, they wrote a book. So in this, they studied the density of states. They gave a precise formula for that in this case. They studied the irreducibility, showing that the block and the Fermi varieties are irreducible, typically. They studied the smoothness of them, where are they smooth and where are they singular. And their results was using a toric compactification in the Trelli theorem about curves, classification of curves. Well, this impressed the mathematical world at that time because in 1992, Peters, who's an algebraic geometer, he gave a Bourbaki lecture about this. And I recommend reading his lecture instead of their book. It's a little clearer. And there's later work which redid this in a somewhat simpler manner by looking at a somewhat better toric compactification. So this toric compactification, they took the wrong, I would say they took the wrong toric variety and then they blew things up a little bit. There's a correct toric compactification given by the Newton polytope, and there's a student of Trubwitz who did this called Batig. And in doing so, he was also able to extend this operator from something that acts on the torus to something living on the whole toric variety. And so that's also kind of interesting. There's some information there that you can get. Anyways, this, even though this happened 30-some years ago, there wasn't much since then. I should point out that around this time, Mumford and with a collaborator, Van Moorbeke, they studied this in dimension 1, and they were looking at directed graphs, and they got a bunch of very nice results relating this to facts about the moduli space of curves, and particularly with maps to P1, because in that case the block variety is a curve with a map to a P1. So let me say a little more about this physics conjecture that I talked about. It's a conjecture of one of my colleagues at Texas A&M, but because it's just assumed in physics, and he pointed out that this is an assumption which may or may not hold. And so again, if you have the spectrum, which is the image of the block variety. This is a different block variety, and every edge of it, every endpoint of it, called the spectral edge, it's the image of some critical point of this function lambda on the block variety. And the spectral edge's conjectures posits, among other things, that generically, meaning for generic parameters, because there's a parameter space here, these critical points are non-degenerate, in the sense of Morse theory of a non-degenerate critical point. And so one step is to study all critical points. So that's an approach that we took. You want to write down equations of them. So the first step is implicit differentiation of just this, of the equation defining the block variety. You get the usual formula we teach people in calculus, and then thinking about a little, you can write down this system of equations for the critical points. So it's of the function lambda, and an observation is because these are toric derivatives. They don't change the Newton polytope. There may be some terms that go to zero when you take the derivative, so it just deletes some points in the polynomial, because monomials are eigenfunctions for these toric derivatives. So all polynomials written here, they support a subset of the Newton polytope of this dispersion polynomial, and so this old theorem of Kuchment plus monotonicity and a little extension shows you the number of critical points is at most the volume of the Newton polytope. That's already I should say that there's sort of an interesting side that happened from this. That when I was first doing this, I started talking with Paul Breiting and other people about I hadn't thought about using Kuchment theorem. We proved this originally using or studying this using Bernstein's theorem that tells you exactly, there's a criterion for when the number of zeros of a polynomial system achieves this bound or not. It has to do with solutions at infinity. And then people interested in polynomial optimization have been proving that a lot of optimization problems achieve this BKK bound by studying solutions at infinity. That's been rather fruitful, but it actually started with this problem. Okay, now I'm really cruising through this. Everyone's really tired, or maybe I'm just loud and fast. So I'll pause. Okay, I'll just pause for a second. So what I want to study these critical points. We have these equations, and there's this standard bound, and we're going to study whether or not this bound actually holds, because this is not a general set of equations. I simply have this polynomial is not even a general polynomial with its support, because it comes from the determinant. It's a characteristic polynomial of a matrix that's highly structured, and it already is. It certainly is not a general polynomial of that support, because it's a characteristic polynomial. It comes from a determinant. For instance, if you're at high enough dimensions, it has to be singular, whereas a typical hypersurface is smooth. Simply because the determinant hypersurface is singular in codimension 4 in the ambient space. And so if you're larger of dimension, you can't avoid singularity. So this is definitely not a general. That polynomial is not general, and these other ones all depend upon it. So it's not clear that you're going to this is not a general system of polynomials. You can't apply. We have a bound, but we don't know if the bound is achieved. Yeah, that's what I should point out. That's very common in optimization, and this is similar because we're looking at critical points of some operator on some hypersurface. I mean, it's like an easy mistake to make that if your original polynomial is general, you assume that this optimization problem will have all the expected number of solutions. And there are published papers that make that assumption. Anyways, so I'm going to talk about how one way to study this is actually fairly easy in this setting. Well, one of the reasons that we study Newton polytopes is because that provides us with a natural ambient space to this compact, in which to study objects. So here we have this dispersion polynomial, and it has a Newton polytope. So here's just a picture of one. they're always pyramidal because they're a characteristic polynomial. So there's going to be lambda to whatever highest power you expect at the top, and then some base at the bottom. And that's, I mean, they're not pyramids. This is not a pyramid, but they have this form that well, I won't try to define that. So now the block variety lives in the complex torus across the complex numbers, but it's naturally compactified by a toric variety corresponding to this polytope. The point being is that there are natural directions at infinity, in this hypersurface, and they're best and they're proper. They're well encoded by the facial structure of this polytope. The base of the polytope is already in my variety because the lambda variable is c and not c star. And so we're going to look at this inside of this projective toric variety because it's projective since it's a polytope. And these critical point equations that I had before, which all their monomials lie inside of the Newton polytope, it corresponds to just a linear section of this. That's this. I mean, for algebraic geometers, this is you have a projective variety. You can look at it in projective space. Then for people in mathematical physics, this takes some doing to convince them of this. But this allows us to study this as this linear section. And now there's a fact is because once you compactify, as you know, I mean, you can run but you can't hide in projective space. So you have a system of polynomials on some open subset of a variety. You get or any functions. It could have fewer than expected number of solutions. But if you compactify, they're going to have to be there at infinity. If you don't see them, they're at infinity. So you can't hide in projective space. And so the number of critical points is less, meaning those which are inside of the toric variety or in your original space inside of this polytope. It's less in that volume. Only if and only if there are solutions to these equations on the boundary. I mean, I should say when Bernstein proved Bernstein's theorem, this was the crucial part of his theorem, was identifying when something is degenerate in this sense. But here's a little bit simpler because I have a toric variety, and the boundary of the toric variety, you just simply you simply remove the interior from it, and what this is this has a nice decomposition to orbits of the torus, one for every face of this polytope that's not the base. And yes?
Could you explain why the critical point equations give you a linear section?
Oh, well, yeah. Well, the point is, okay, so I have a polynomial. Okay, so I like to explain this way. I'm talking to people in math. I have a polynomial, or a system of polynomials in C star. It's a nonlinear equations. Okay, it's hard. It's on an easy space. So what we do instead is we make the equation simpler, but make the space more complicated by simply so every monomial you see in your the equations need to have the same support for this. Every monomial you have in your polynomial, you have a map from C star to the D or C across C into some space. You simply take the list of monomials. That's a monomial map. Think of the Segre embedding, for instance. Okay, and then and what happens then is a polynomial of those monomials becomes a linear section of projective space pulled back. Yeah, sorry.
Yeah, that makes sense.
Well, I should have. One time was in a completely different setting. I was talking about this with Percy Diaconis, and he didn't let me get past that for 20 minutes. So it's important. It's an important thing to think about. But we do this all the time. You have a vector bundle. You have a line bundle. You take sections of it. You get an embedding, and your sections are just pulled back in the hyperplane section. So if you prefer something that's really abstract, you should think about it that way. But it's also incredibly concrete in the setting. I mean, in fact, one of the reasons that toric varieties appear a lot outside of algebraic geometry or in applications is because of how insanely concrete these objects can be. Yes?
I have a question since you said we had some time. You started out assuming that the operator is self-adjoint.
It turns out it's as I defined it, it is a self-adjoint operator.
Okay.
I mean, on this graph, okay, so if you have, I mean the pairing is simply between two objects. It's f at u times g bar at u sum over all u. That's the pairing that gives you the
Because you
altitude space.
choose undirected graph.
What?
Because it's undirected graph.
Well, okay. The original operator was. Yeah. It's because it's undirected. But I mean the point is, because it's undirected, the operator acts in both directions. So when you're essentially transposing the matrix, and that is the same. When you get the same influence. Okay. Oops. Yeah. So I'm going to write BV for this complexified block variety, and I'm going to study the critical point equations on it. Or rather, I mean the critical point equations. There's a hypersurface that gives us the block variety, and then there are all the other ones which are also linear sections. And well, as I explained, each face of this Newton polytope gives us a torus orbit. It contributes a torus orbit to this toric variety. I mean, I really like this because you can just hold up a polytope and point to it when you're talking to students about what a toric variety is. Now, the Newton polytope and its base give us the ambient space that we started out in, and all the other stuff gives you all the other stuff. All the other faces give you all the other pieces. And so the boundary of this of this toric variety, as I defined it, it's the disjoint unit of these orbits, one for every face, every proper face that's not the base. And a little bit of analysis, so we can start to look at these equations on each face. And the first thing to observe is that if your Newton polytope has a vertical face, like this one that I drew, then the critical point equations have a solution in that closure of that, which is just a toric variety corresponding to that face. And the reason is well, okay, I wrote down something fancy, but if you take a direction normal to that face, which annihilates it, then the restriction of your polynomial to that face is homogeneous with respect to that direction, or quasi-homogeneous, and that means that yes, I mean, so typically you restrict to find out what something is on a face, you just restrict the polynomial to the monomials in that face, and now you have n+1 polynomials on something of dimension. Well, you have something of dimension n or less. But if it's quasi-homogeneous, because the quasi-homogeneity, it works out perfectly, you'll always get solutions on the closure of that face. Because of the way quasi-homogeneity works is you lose independence of your polynomials because of restricted to the face because of this. So there's always going to be faces, there are going to be solutions on the face. And if the face is not vertical, it was actually a really pleasing exercise to discover that if it's not vertical, then you have a solution on that, you have a critical point on that face with these equations, if and only if it's actually a singular point of the block variety restricted to the face. So in this case, a singular point at edge would be a double root, and a singular point on one of the facets would be a curve with a singularity. And so we deduce that there's a relatively reasonable geometric condition as to whether or not the critical points are equal to the quantum with multiplicity are equal to the volume of the Newton polytope, namely if there are no vertical faces. And if the block variety affinity is smooth, and these are, the vertical face is fairly easy to understand. Smoothness might be a little bit harder. I'll explain. So, when I dipped into this work, in my talk I talked about we wanted to look at the study of the critical points first, and I'll explain what we can use our knowledge for. After I go through this, so maybe that's giving you the candy after the medicine instead of the other way around. We have this theorem, and the question is, can we? Is there a class of graphs for which we actually know that this, that these two properties hold? The vertical faces is not so hard. I can draw these all day. And there is a class of graphs which we're able to prove something about. We call them dense periodic graphs. So, okay, there's a one-sentence definition which doesn't tell you much, but it gives you the idea. A periodic graph is dense if it has maximally many edges given its combinatorial structure. So let me explain to you what the combinatorial structure is. Well, I have this graph with a z to the action. I can fix a fundamental domain for it. or I will fix a fundamental domain for it. And then the support of that graph is simply, I look at all the edges that are incident on the fundamental domain, on something in the fundamental domain, and they either stay in the fundamental domain or they leave it. And if they leave it to a translate of the fundamental domain. So I just record all those group elements. So those are monomials, and I'll call that the support. And it's a natural notion to use the word support because it contains the support of the entries in that matrix. So the support of a polynomial is the exponents of its non-zero monomials, of the monomials you actually see. And a graph is dense if whenever you're in the support, the restriction to the fundamental domain and its translate is a complete graph. So that's a maximal number of edges you can have given that combinatorial structure, namely the size of the fundamental domain and that there's exists an edge leaving it to somewhere else. So every graph embeds in a minimal dense graph. So here is an example. This is the hexagonal graph drawn not so symmetrically, but if you demand that you have your translates be orthogonal, that's what it's going to look like. And then here's its here I get a dense graph. So you see between there's an edge here, so I have to draw in the other three edges. And also and hence this is an example of a dense graph with the extra edges drawn in, and this is the support. It's simply this two-dimensional cross polytope, which is centrally symmetric. Now, okay, so if I let E be the set of orbits of edges in a graph, then I can write down a parameter space for all the possible operators and all the on that graph. Namely, I have one parameter for every edge orbit and one parameter for every vertex orbit. That's what Y is. And the spectral edges conjecture, it posited that there's, I mean, what it really says, or what it should say, because it's kind of formulated different ways in different places, is that there's a Zariski open subset of Y for which these spectral edges are non-degenerate. So now, for any graph, I'm going to define a Newton polytope of that graph, and that's simply the generic Newton polytope. So it's not hard to see whether this holds because you look at this dispersion polynomial with the parameters as variables, and you look at the monomials you care about. Each one of them has a coefficient, and you demand that none of those vanish. So that defines a Zariski open set of your parameter space. And so there's a dense open set, non-empty, consisting of parameters, so that you have the expected Newton polytope. That's true for any graph. Now, if the graph is dense, then the Newton polytope of this generic polytope is simply a pyramid. So this is an example for the dense graph that I showed in the previous slide. And now, when D is 2 or 3, but it does not hold for 4, both for obvious reasons and also the proof breaks down, which is satisfying. Right? If something is false and you don't know where your proof breaks down for it, it should be troubling. You can shrink the open set, and you can choose. So for parameters in that open set, that the block variety is smooth at infinity in the sense that I talked about. So there are no vertical faces because it's a pyramid, and it's smooth at infinity, and that requires. In fact, what we end up showing is that we find a specialization of the parameters for which it's smooth at infinity, which we can prove directly. And so for this class of graphs, the number of critical points is the volume of the Newton polytope, and there's a formula for it. And the formula is in terms of the support of the graph, and it's just scaled by this factor. So there's no, which if you've proved what the volume of a pyramid is, you'll understand why there are no n or d or d plus 1 factorials lying around. So let me give an example. So it's a fairly easy fact that a critical point is regular that means that it's a non-singular point on the block variety. So that's what I mean by regular critical point, and that implies that it's non-degenerate in the sense that of this non-vanishing Hessian. That's not so hard to do. And so here is a Z2 periodic graph with the support into a polytope. It actually looks like a child scribbling when you draw these because the edges just overlay each other. But there's some structure there, and that's a support, and there's this Newton polytope, and so Matt and I, since we use different computer algebra systems, independently found parameters like the first ones we tried, which find a block variety which has exactly the correct number of regular critical points, and that implies the spectral edges conjecture for this whole graph. So let me explain that. I should say I got into this because I was approached by a graduate student at College Station if I could tell her something about the solutions to a set of equations she emailed me. And after using Bertini, I decomposed it into irreducible pieces, realized most pieces are non-physical, like the z variables were 0, and the physical piece I had the correct dimension. And so we later wrote a paper which this is for the dense graph I showed a little while ago, whose purpose was to show this spectral edges non-degeneracy conjecture for that graph. There's a theorem in this paper which essentially says that this conjecture either holds generically for all for generic set of parameters, or it fails generically. And that's an obvious statement as an algebraic geometer that if you have an algebraic property on a family, it either holds generically or it doesn't, because it's but that was of deep interest in the mathematical physics community. Results like that are called arbitrage, where you have one thing, it's very cheap to you, the idea is dear to other people, and you bring it to them, and you get the utility difference. For those of you who study economics. Now the second part of the paper that I did the calculations, what a numerical calculation, despite how wonderful it is not a proof, and you need and if you write a paper, you should probably prove something if you claim it. And so what we realized was that if we could show that if we had a bound for the number of solutions, the critical points, and we found a point that had that number of critical points, then nearby, in the usual topology, it's a covering space. And so then if we show that these critical points are non-degenerate, then the locus of parameters for the degenerate critical points has to contain a classically open set, and hence is Zariski dense. That's also fairly obvious. The best part is because I'm in algebraic geometry, I did the calculation of positive characteristic, which we did not admit in the physics journal. As you know, that's a perfectly legitimate way to prove something. And so once we have this result with Matt, we at the end of the paper we show examples like this where we can use a single calculation in whichever characteristic you want, and then it proves the spectral edges conjecture for that graph for all the parameters. But there's more. Here's a graph. It has 3 vertices in the fundamental domain, and it's more sparse. It's missing, I think, 19 edges. I explained that. There's this support and there's this Newton polytope. You can see that even on the facets of this polytope, that's of height 3. Normally you'd expect 10. Is that right? 10, yeah, I think 10 monomials on each of those facets, but there's only 4. So it's incredibly sparse. But our calculations find a block variety with the expected number of regular critical points. And in fact, in each facet, what you get is a genus 1 curve, I think. That's the usual, a smooth one in that case. Now, the graph is not dense. It's missing 6 edges in each direction and 1 in the fundamental domain. So there's 19 missing edges. But just simple upper semi-continuity, because this is the same Newton polytope as a dense graph, tells you every graph with more edges that in the parameter space, there's a specialization, namely to these guys, which is smooth and has the correct number of critical points. So therefore, the general one in that family has the correct number of critical points. So it implies 2 to the 19th examples. So that was sort of a nice, fun observation. Now I'm going to close early because I speak really fast. But sorry, Anyways, so I'm going to talk about some work that's going on now, or going on with Matt Faust, Jordi Lopez. He's here in the audience. He's also wearing a cool shirt. Stephen Shipman, who's a mathematical physicist at Louisiana State. Jonah Robinson, a master's student, and Wen-Sun Yo, who's one of my colleagues at Texas, who's an analyst. One of the things we're studying is so I described how you embed this, you look at this block variety in a toric variety, and that allows you to deduce some information and get further than you might otherwise, or at least prove things. But we're studying more generally toric compactifications, in some cases some disingularizations, although that's a little vague. And our goal is to understand, one thing is to understand that we have an operator that's defined on actually a trivial bundle over C star across C star to the D across C, and we like to extend it to the boundary of the toric variety. And that may include some modifications we don't know, because then we'll have a map between sheaves, actually trivial bundle on the toric variety, and try to exploit that a little further. Question is, how do the number of critical points, et cetera, depend upon the graph? One question that we're looking at is, when you have a vertical face, you're always going to have some critical points on the boundary, but you have the number of critical points inside, and so it tells you the Newton polytope is the incorrect object to look at for counting these. You need to look at a Newton-Kunkov body. There's homological invariance of this matrix of Laurent polynomials, or the extension, and what do they imply for spectral theory, maybe beyond what this student did. There's also a question of parameter identification. How much do Bloch and Fermi varieties determine the graph or the parameters? There's a fair number of results about Bloch varieties on this. And then there's also, I think it's a little harder because our techniques are not sort of set up for this, is to study the spectral edges conjecture in dimensions 2 and 3, and including treating singularities. There's a type of singularity. Because we have a determinant. I have a subvariety of a matrix space, and I take the determinant along that subvariety. If the subvariety meets the singular locus of the determinant, it's going to be the block variety is going to be singular. That's just how the world works. But the determinant, if you take a look at a generic singular point, it has a fairly nice structure. I guess in dimension 3, it's like the usual circular cone. And points like this that are ordinary double points that are called Dirac points, and they're a great deal of interest in mathematical physics. So understanding when we get those or why we must get them, because there are examples where you're forced to, so there should be some sort of obstruction theory or some invariant that tells you you have to. These are some other things to think about. So this is some further work that people are doing, and certainly there's a lot. Right now, many of the people we know in mathematical physics are exploiting this Newton polytope structure to study some of these questions about irreducibility. And here's some sources, and I'm done with 11 minutes left. I harassed 4 speakers, and no one gave me the 3rd degree.
I tried. You have an answer.
Well, you could keep trying. Go ahead, Peter.
So one slide back. What do you mean by homological invariance of your matrix and polynomials?
Okay, so I have a map between 2 modules. Okay, but it's sort of a Laurent ring, so it's not like Betty numbers or something. But you can ask about the kernel and the co-kernel or some resolution or some information like that. That's what I mean by homological invariance. I have a map between, in particular, the kernel so I have this kernel of this operator is a sheaf that's supported on the block variety, and it's the sheaf of solutions. And you know, and so I mean, people sort of care about that, and I think you can study that using some of the methods that people have in computational cognitive algebra or in algebraic geometry.
Do you expect these things to be computable over the way? I don't know.
Well, I can just press a button on my computer or ask a student to do it and they get an answer. Yeah, I mean, yes, in individual cases, but also these are highly structured systems, you know, determinable varieties, in which we can study them, you know, in general as well as just like, you know, pressing the resolution button on your computer. I mean, I should say that this work was all inspired by computation. I mean, I fed Bertini a bunch of equations and then I tried to interpret it. Bertini, by the way, is a system that uses numerical analysis to solve systems of equations, and in this case, it uses it to decompose the zero set according to the dimension and the degree and the irreducibility, which is really, I mean, there are other systems too, but which is really a super tool if you don't know what's going on.
Yes, please.
So, you thought about the situation where the potential satisfied additional symmetries, like for a larger group.
Oh,
I know that in condensed matter physics.
oh, that's super interesting. I mean, when I was in Leipzig last spring, and I spent like an afternoon talking to a mathematical physicist who was interested. Yeah, I mean, when we have an actual crystal, it doesn't just it usually is more than translational symmetries, and they actually look at these objects. So these objects will be they'll be symmetric with respect to the symmetries. They look at them within just a fundamental domain of the finite group action on a fundamental domain. Yeah. So but I mean, yes, one can. I have not. I mean.
Because in that situation, for instance, they associate classes in equivalent cases topological cases. So they are topological.
Yes. Yeah. I'm not doing that yet, but I mean this. Yeah. But you know, the one point. So in analysis, you get these objects that are maybe hard to study, but when you discretize, they become an object in algebra that we have tools to study, and you can either believe the physicists that they want to do this, or you can just pretend this is important and just do it yourself. So you can choose your way. I'll follow the professionals. But the point is we have methods that are not available in analysis, but to get some additional information about these objects.
Could you say again what else there was to check once you found one system?
Oh yeah. Okay. This is something I want to show that I have a parameter space. I want to show that generically there are no solutions to some equation, the equation for a degenerate critical point. Okay, I'd like to show that for a typical parameter. So it suffices. Okay, you think it would suffice to find one, but that's only if you know that the neighborhood of that point. It's suffices to find one point where there's no solution to these equations, but only if the neighborhood. But you have to make sure that the map of this. There's an instance, right? You have to make sure that map is proper in order to make such a conclusion. So we know that there's an instance variety from critical points to parameters, and it's something to one, as an algebraic map. If I find a single point where I have this many points in the fiber, then I know it's a proper map in the neighborhood of this point. Right? These are affine varieties. You could just be missing something as it goes off to infinity. But once I know that, if I know there are no solutions to the other equations, then I know there's a neighborhood at this point for which there are no solutions to these critical point for the degenerate equations, and so that's a Zariski open subset of the parameter space.
So I was thinking, if you know the upper bound in the compact space is the volume, and you find somewhere volume many regular points.
Exactly. Yeah, that's exactly what we did. Yeah. I'm sorry, but I was just sort of explaining in minute detail what the argument might be. I mean, I have to do this with referees.
Is it at all interesting to figure out, like, what parameter values are non-generic?
That is kind of interesting. It's actually hard. Okay. So first of all, there's a generally difficult problem in real algebraic geometry, which we call the geography of parameter space. You have some system I don't know what maybe your parameters with your models, and you like to know where are the degenerate maximum likelihood estimators. Okay, that's a hard problem because there's like a discriminant. You look at real points. There's a complement of the discriminant. You want to know what happens in each component. That is a hard problem. So it's even harder here because here we have these are real algebraic varieties, but the space we're working on is this compact torus. And that's a non-standard real structure. And it turns out if you just feed this into ordinary software, it's going to go belly up like a fish in like a dead fish in your fish tank. It's not going to be able to do it because the algorithms are not very well adapted to this. I mean, I've had a lot of trouble trying to study these. So we actually have a project with Simon and Maggie Regan, who I should have listed up there too. Sorry, old slides on. So where the goal is to like just compute examples because it's actually already hard. I mean, it was surprising how difficult. I was trying to do something last fall. It's surprising how difficult this was because the tools are not there. I mean, okay. So the unit complex numbers that's a real variety, and you can embed you can embed C star into C2 as x as 0 set of x squared plus y squared equals 1. The circular points at infinity are the 0 and infinity of C star, and the unit circle goes to the unit circle. But what you've done is you put something that's codimension 1 and degree 2. Now take a d-dimensional torus, and you have it's dimension d and codimension d, and degree 2 to the d, and this is clearly the wrong way to go. Or rather, it makes it very complicated. So it's a little bit of a challenge. What do you do? How do you do real algebraic geometry in the face of non-standard reality or alternate reality that nature gives us? Unitary groups, Hermitian matrices, these are all different reality that we need to do from applications. So does that answer your question?
Yes.
I mean, I've hinted at that a little talking to you this week. Yeah.
Are there any other questions?
So Frank, so you compute everything
Finally,
for
a speaker.
E equals to,
What?
I think it was like slide 11 or something. So you
Okay.
have like only d equals 2 and d equals 3.
Yeah, where's this? There it is, yes. Yeah, well, the reason is okay, by dimension, okay, I have a determinant. And when D is 3, I have a 4-dimensional space. So it's a 4-dimensional space of matrices. I take the determinant. There are going to be singular points. But on the boundary, I can show there are generically no singular points. So that's the restriction. If D is 4, there's, yeah, I mean, in fact, to study this, well, even in R3, you have to come to grips with how do you handle sections of the determinate hypersurface that are going to emit the singular locus. A couple of my colleagues are using stratified Morse theory to begin to understand some of this, which I thought it was pretty cool.